看值就可以了。
可以了吗？
可以。
Okay, can we start now? Okay, thank you, Justin. Good afternoon. The title of this presentation is Uncovering User Interest from the BIOS and the Laws the Watch Time in Video Recommendation. My name is Haiyuan Zhao. This work is co-authored with my supervisors in Renmin University of China and Huawei Loas Arc Lab. So let's begin. In video recommendation, users' watch time is commonly adapted as an indicator of user interest. And compared to the binary click signal, the watch time is a quantitative indicator, which can better reflect the user's interest. However, we should also realize that the watch time is not always reliable. It also suffers from the duration bias and noisy watching. For duration bias, it means users tend to spend more time on videos with longer duration, regardless of their actual interest level. We should look at the figure A. In figure A, all three videos are liked by the users, but we can see that the longer videos have laterally longer watch time. For the noisy watching, it means users need some time to determine whether they like a video or not, which results in spending time watching videos they do not like. For example, in figure B, the users may be interested in the beginning of this video. However, as the time goes by, she will finally find that she's not actually interested in this video. These two problems makes the watch time not a reliable indicator of user interest anymore. So we also find some evidences from the real-world dataset to support the existence of the duration bias and the noisy watching. In figure A, it shows the mean watch time of records with positive explicit feedback in different durations. These records, they have the same user interest level, but they don't have the same watch time. Instead, their watch time increases with video duration. So this supports the existence of duration bias. In figure B, it shows the mean watch time of records with selective explicit feedback in different durations. These records are disliked by users. However, their watch time is non-zero. So they support the existence of noisy watching. So current methods like the play complete rate and watch time gain and quantile-based method, this method proposed to transform the watch time into user interest using different assumptions. However, they primarily focused on the duration bias while ignore the impact of noisy watching. So this may limit their effectiveness in uncovering user interest from the watch time. Next, I will give the problem definition of the video recommendation. So the dataset D consists of the user video feature X and the watch time W and video duration D. And our target is to learn a model F for predicting the user interest R. Usually, we can adopt a cross-entropy loss to fit the prediction on user interest R, so we can call it the ideal loss. However, since the user interest R is unobserved, what we can observe is only the bias and the noise, the watch time. So we call it the live loss. Then we analyze the watch time in a causal graph. As we can see, the path from X to D and R shows the video duration D and the perceived interest R are dependent on the feature X of video and user. The path from R to W shows that the watch time W is determined by the user's interest R. And the path from D to W shows that the watch time W is also affected by the video duration D, especially when the R equals to 1. That means the user is completely interested in the recommended video. So what the recommendation model needs to estimate is the effect from X to R. So based on the causal graph, we can decompose the expected watch time into two parts. As we can see, this decomposition shows that the watch time can be treated as a mixture of the user interest and other bias and loss terms. When R equals to 1, this conditional expectation terms denotes the effect of duration bias. When R equals to 0, this conditional expectation terms denotes the effect of noisy watching. Once we know the true value of these bias and noise terms, we can definitely separate the user interest from this observed watch time. Meanwhile, it also shows the gap between the watch time and user interest. It consists of two parts. The error caused by the duration bias and the error caused by the noisy watching. So we have to consider both the duration bias and noisy watching when we need to uncover the user interest from the watch time. So let's introduce the method we proposed. So based on our causal analysis, we first need to estimate the bias and noise terms from the watch time. Note that we can treat the watch time distribution of duration D as a mixture of two conditional distribution. And the expectation of these two conditional distribution are bias and noise terms that we need to estimate. Moreover, in the real-world dataset, we also find the watch time presents a bimodal distribution. So this supports us to use Gaussian mixture model for estimating the bias and noise terms in each duration group. So then we consider that the records with similar durations should have the similar bias and noise terms. So we also employ a moving average to smooth the estimated bias and noise terms of different duration groups. After we have got the bias and noise terms, we begin to separate the user interest from the watch time. And we call it the debias and the denoised watch time correction, or we can call it the D-squared code. As we can see, if the bias terms and the noise terms are estimated accurately, we can obtain the unbiased user interest from this equation. However, we cannot avoid the estimation error of the bias and noise terms in most cases. So for reducing the effect of the estimation error, we try to reduce the sensitivities of the bias and noise terms in the D-squared code. So we also propose a sensitivity-controlled correction function. We call it D-squared code S. We can prove that in this formulation, when the alpha less than 0, the D-squared code S can reduce the sensitivity of the bias term. When alpha is larger than 0, the D-squared code S can reduce the sensitivity of the noise term. So the best value of alpha depends on which the bias and noise terms dominates the whole arrow. So our experiments are conducted on the two real-world datasets, the Quirand and the WeChat, which is from two famous short video platforms. Since we cannot get the Oracle user interest, we choose to use long view label in the Quirand, which is defined as this. And our evaluation metric are GAUC and NDC-ZK. So our experiment is conducted on 3 different backbones models. For presenting the advance of our method, we also equipped the current methods with some denoise ability, which they did not consider that when they designed. So we can say that our spherical S can underperform other baselines on 2 datasets and 3 backbone models, even for that the noise baselines. Then we also investigate the effectiveness of mitigating bias and noise. These 2 figures show that bias causes error and noise causes error in different duration. Note that in the quadrant, the duration bias always dominates the whole error in all the duration range. And in the WeChat, we find that the noise watching dominates error in longer videos. Then we also divide the dataset into 3 different duration groups, and we conducted the evaluation on different duration range. So we can see the results. Our spherical S outperformed other baselines in all duration bins, which shows the effectiveness in mitigating the duration bias. We can also find that our spherical S also outperformed the other baselines in the longer video of WeChat, which we have shown that the noise error is dominated the whole error. So this result shows that the effectiveness of our method in mitigating the noise watching. So we also investigate the effectiveness of our proposed sensitivity control technology. This result shows that our sensitivity control version can further improve our model's performance in both 2 datasets. Finally, we also conducted an online A/B testing for our spherical S by deploying our model in a popular browser, a platform with tens of millions of daily active users. The 7 days results shows that our method can largely improve the user experience in the real-world application. So let's conclude the contribution of this work. First, we analyze the existence of the duration bias and noise watching in the video recommendation. And we also provide a unified causal view for modeling the bias and the noise. Then we propose the spherical method for mitigating both the duration bias and noise watching. Spherical provide a way to uncover the user interest from the observed watch time. Finally, we conduct the offline experiments on 2 public video recommendation datasets, and we also conduct the online A/B test on the real video product. Our results verify the effectiveness of our proposed method. So that's all. Thank you for watching.
Great. We have time for questions, which you can either submit online via Slido or come up to the microphone here. While we wait to see if there's any other questions, I had a question, which is, I know you kind of motivated this from looking at short form video, but I'm curious if you think these concepts would extend to longer form videos or potentially episodic videos where there might be kind of breakpoints. Do you think you'd have to do any modifications for that type of setup?
Yeah, actually, I analyzed the video length. I can switch the slide to this one. So I analyzed the video length from the range from 0 seconds to 250 seconds. So I think our method can perform effectively on the longer video, even for the 6 or 4 minutes. Okay.
And then the other question I had is, like, people's interest in a video might vary across time, right? So it might be that the initial part they were interested in, and then something kind of changed in that. So I'm curious if you have any thoughts on how you might modify that to handle interest shifts over time.
You mean the user's interest maybe change over time?
Yeah, maybe they loved the first 10 seconds, but then something happened and then they lost interest.
So I want to say that this point is over the scope of this research. So we maybe consider this question in our future work.
All right, let's go over here.
sorry, that works now. I'm a little bit confused by how these parameters are trained. You mentioned they're using ground truth label from another definition.
Yes, yes.
But how do you, like, if you go back to the ground truth definition, that's, I'm a little bit worried you're overfitting to that just definition.
Yes. Actually, it's quite difficult to get the Oracle user interest. Since we can already observe the interactions, the user behaviors in our data log.
Yeah.
There is no true user interest label. So we try to adopt this long view definition that described in the query dataset as a ground truth. So this may be one disadvantages of this research, but yes, we cannot find the Oracle user interest label.
I see, thank you.
Yes.
Hi, thanks for the nice talk. Extending on Justin's question from earlier. So here, like, you define long videos at the range of 240 seconds. But when we talk about like movies, let's say, with the same trends hold up when we're talking really long videos?
Yes, really long, maybe 1 or 2 hours, like a movie. Yes. So in this work, we just focused on the short videos of our short video platforms. So I guess in longer videos, there also exists some noisy watching and duration bias. So, but now in this work, we did not conduct our method on the so long videos. So maybe we can verify the performance in more longer videos. Yes.
Do you think any significant adjustments would need to be made to do that kind of evaluation on longer form video, or with the same approach? Just
pardon me? You mean?
Would you need to make any significant adjustments to the approach to evaluate it for the longer form, or would it just do the same thing but on longer videos?
In my opinion, I think since it also exists the noise watching and the duration bias, I think the main form is quite similar to the method are proposed. But I cannot say that there is only duration bias and duration bias. Maybe there exists much more questions and challenges when we face to the longer videos. Maybe it refers to the psychology of the human's mind. Yes. So I think maybe we can try. Have a try. Yes.
Okay. Thank you.
Thank
Cool.
you.
So there's one online question from Nava. WeChat noisy watch error is larger at longer durations. What do you think is the cause of this? Are these people who fell asleep or left the player on?
Yeah, I think it's mainly affected by the quality of the content. Maybe when you recount the bad videos, people just need to watch a few seconds and switch on the next one. So if your content is too bad, there is a lot of noisy watching. Yes.
Awesome. Take one really quick.
Hey, hi. Thanks for the nice talk. So the video consumption pattern could also vary across the categories.
Pardon me?
So the video consumption pattern could also vary across the different categories.
Different what?
Different categories like.
Oh, different category. I know. My apologies.
So yeah. So how do you take that into account? And yeah, what do you propose for the same?
So in this work, we just get it together and did not consider the categories of different videos. We just focused on the watch time of all categories of video. We think that there exists both bias and noise in all the categories of video. So maybe you can conduct more fine-grained research to discuss different video. I believe that maybe when people face on the food video, they may have a more severe duration bias. Maybe on other videos, maybe suffers from more noise watching. So it's a fine-grained research.
Cool. Thanks.
Awesome. Let's thank our speaker again.
Yes.